Okay, this is a perfectly valid, probably more valid, more intuitive than most definitions of the cross product. This will work if you do it correctly. It'll work every time if you follow the rules for just multiplying I and j. However, there's a more efficient way to write this out and do it. Sometimes your book will give you a formula, and it's kind of a hard formula to keep track of. This is easier than keeping track of the formula. This, I believe, is the most convenient and easiest way to calculate a cross product. And that's simply, we write a matrix, 3 by 3 matrix, first row being I, j, k, second row being the components of the first vector, in this case the A vector. Components are 2, 0, because there's no j, and 3, negative 3, 2, 0, negative 3, standing for 2i, 0j, negative 3k. And then the B vector is 4, 3, 2, standing for 4i plus 3j plus 2k. Now that determinant is easily enough calculated. And I assume that in your prerequisite courses, this is done in typically in pre-calculus 2 and elsewhere. If you don't have it, if you have trouble following this, please let me know. I can give you references. I can give you a quick explanation. Okay, so we have I, and then we multiply that by the determinant, and I'll indicate determinant just with kind of an absolute value sign. 0, negative 3, 3, 2. And then it's minus j times the determinant of 2, negative 3, 4, 2, plus k times the determinant of 2, 0, 4, 3. Now each of these 2 by 2 determinants was found by simply, I times the determinant that we get if we eliminate the column below I and, of course, eliminate the first row. That leaves us with these 4 numbers, which constitute this determinant. And then for j, we just eliminate the row below j and take the numbers 2, 4, negative 3, 2, and very similarly with k, eliminate the row, etc. 2 by 2 determinant is very easy to calculate. We just multiply these numbers, we subtract this product from this product. So it's just 0 times 2 minus negative 3 times 3 gives us minus negative 9. So that gives us negative 9i. Make sure I'm still visible here, okay. And then minus this determinant, 2 times 2 is 4, negative 3 times 4 is negative 12, 4 minus negative 12 is 14. 14, We'll figure that out in a minute. So that's minus j times 14. Notice the negative 9i, oh man, it's positive 9i, it's negative 9, positive 9i. But I've got 14 here where I've got 16 here. What did I do? Got 4 there. Well, we'll have to check that out. There's a discrepancy here. I've either written something out wrong, probably almost certainly written something out wrong, but let's continue. Then k times 2 times 3 minus 0 times 4, well, that's just 6. So that's plus 6k. Now, except for the fact that I've got minus 14j where I should have minus 16j, this reconciles. So I'm going to just turn off the recorder for a second and figure out what I did. Okay, that didn't take long, but it took longer than it should. I've got 4 and 12 here, so that comes out to 16. Just obviously can't do simple arithmetic. As you can see, this scheme is much more efficient than using the distributive law and having to get all the rules right every time. Now, what's the significance of the cross product? Well, you're going to understand that there is some significance because it comes out of this model of exerting a torque on a rotating object. It has many, many more applications. We're not going to talk too much about those applications now because we just want to get you to the point where you can calculate these cross products. But there is one thing you do need to know, and you need to know that the cross product of A and B has a magnitude that's equal to the magnitude of A multiplied by the magnitude of B multiplied by the sine of theta, where theta is the angle between A and B. Now, the sine of theta is 1 if theta is 90 degrees. So if I have two vectors that are at a right angle, okay, then for the magnitudes of those vectors, the cross product is going to be maximized. It's going to just be equal to the magnitude of A times the magnitude of B. The other property is that A cross B is perpendicular to A and perpendicular to B. That shouldn't be too surprising, although it takes a little work to prove that that's always got to be true. It shouldn't be too surprising in terms of these rules here. The I and J vector is the product of the I and J vectors is perpendicular to both the I and J. The product of the J and K vector, cross product, is I, which is perpendicular to both J and K, etc. So when you get down to the basic unit vectors, this is certainly true. The cross product of any two unit vectors is going to be perpendicular to both of them. The direction of the vectors is going to be determined by the right-hand rule, and we haven't talked about the right-hand rule, so let's just talk about that for a second. Okay, so here are two vectors. They're not perpendicular. Okay, trying to get oriented. I keep looking at the screen over here. Excuse me, I should be looking at you, but I'd have to get used to this setup. Okay, so here are two vectors. Let's say they're in this orientation. Now, what direction is perpendicular to these two vectors? Keep wanting to use that hand. Okay, well, the plane of these two vectors is here. Okay, so here we have the plane, a little more graceful if I go underneath the plane. What's perpendicular to that plane? Well, this direction or this direction. Okay, anything along this line that's perpendicular to the plane of these two vectors. Okay, so if this is my A vector and this is my B vector, okay, well, we can think back to the idea of if this is my distance from the axis and this is the force that I exert, bring this force out here, it's going to tend to rotate things this way. That's counterclockwise, so it's going to be out here rather than down here. A more convenient way to visualize that is to just take the fingers of my right hand. I'm going to have to turn around to do this because I'm going to be blocking everything. Okay, I've turned around, but this is my A, this is my B. Okay, take the fingers of my right hand on A, and I orient my hand so that when I rotate my fingers, it rotates to the vector B. Now look at my thumb. My thumb is pointing in the direction of the cross product. Again, if this is my A vector, which would correspond to the displacement from the axis, and this is my B vector, if I pull in this direction, I'm going to create a rotation like this. That rotation, from your perspective, is counterclockwise, and it would have to, the cross product would then be a vector in this direction. Okay, the right hand takes care of that. So that's the right hand rule. You can read about that in your book. You can find it all over the internet. You can find explanations, demonstrations. So yeah, make sure you understand the right hand rule. Make sure you know how to calculate a cross product. You should be able to calculate it this way, but when it comes down to the practical application, you're probably going to want to calculate it this way. So you should be able to do it either way. This is a little longer, but it's not difficult. Just distributive law and apply these laws. Here, just apply the calculation of a determinant. One more thing that I didn't mention, should have. If the sine of theta is 0, then the cross product is 0. Now and I hope the computer did all right there, it just went into screensaver. Getting too long-winded, obviously. Okay, well, sine theta is 0. That means that theta is either 0 or 180 degrees, which means that this vector and this vector are going to be parallel. If you go back to the torque idea, if you displace this far from the axis and then pull in this direction, there's no rotation. Okay, or if you push back in this direction, there's no rotation. So at 0 degrees or 180 degrees, you get no rotation. Okay, hopefully that'll serve as a reasonable introduction to the idea of the cross product. There's much more, and if you're taking multivariable calculus, which many students are, you already pretty much know that. But that's going to suffice for right now.